Okay, you guys know how I do reviews. If you remember from last time, I just go through and we go through each topic, but generally I don't review because I don't need to review this, you guys review. So sort of an active conversation. Okay, so the first thing, what was the first thing that we covered on this test? I think we started at chapter 3. Yeah. What was chapter 3 on in general? Vectors, right? Euclidean vectors, right? So like Rn. Yeah. So what was the first thing that we talked about in that set?
Norm, dot product, and distance in Rn.
Sure, probably. I don't remember. So yeah, norm, dot product, distance. So what's a norm? What's the norm of a vector? What does that like represent?
The length.
It's the length, right? This is like the length. How do we calculate it? Yep.
So you basically take whatever vector elements are in U, you square them, and then like you add it all together, but you square root it at the end.
Like this?
Yep. And then square root over all of that.
Yes. Exactly. Yep. Dot product. So say that I have vectors u1, u2, u3, and I want to dot that with v1, v1, v2, v3. How do I do that? Yep.
V1 times U1 plus V2 times U2 plus V3 times U3.
Yep. Exactly. Trying to think, is there another formula for dot product? So if I wanted to calculate arbitrarily u dot v, is there another formula for that?
Yeah.
What is it?
The length of the norm or the length of u
Norm of
times
u.
the length or norm of v and the cosine of the angle between them.
Yep. Exactly. Okay, what about, what was the last thing you said? Distance. What's the distance between two vectors, let's say u and v? Yeah.
It's v minus u and then the norm of that?
Yep. Question for you. Would it be okay if I did the norm of u minus v versus the norm of v minus u? Does it matter what order I do them? No, right? Because the distance from one to the other is the same as the distance backwards, right? Okay. What about some, I think there were some like theorems that were relatively important for these like norms and dot products. There's 2 of them that I can think of, 3 of them. 2 of them are inequalities, and one of them is an equality that you probably learned in like grade 7. Just under a different, well, same name, but it just looks a little different. Yep.
The norm is always greater than or equal to 0.
Yes, that's definitely true. The norm is always greater than or equal to 0. Yeah, but that's true. That's not what I was looking for.
Or the norm of u plus v.
Norm of u plus norm of v, like that,
Yeah.
is equal to, or is it?
Is greater than or equal to
Yep.
the norm of u plus v.
Do you know what that one's called? Yeah.
Triangular.
Triangle inequality, yeah. So that's one of them. There's 2 more that I can think of that are important-ish. One of them is a theorem that you learned in like grade 7. It was probably like the first theorem you've ever done. It has to do with triangles. Pythagorean theorem. So norm of u squared plus norm of v squared equals the norm, I'm making a mistake here? Yeah, norm of u plus v squared. That's Pythagorean theorem. And there's one more that had a funny name. Anyone remember it? No?
Orthogonality?
Sorry?
The being.
I think that's later in the chapter. Cauchy-Schwarz? Remember that one? No? Oh shoot, okay. It's that the absolute value of the dot product is equal to, I always get the sign messed up. It's some inequality, and I'll figure out what it is in 2 seconds here. Norm of u times norm of v. I think it's this way.
Yeah.
Yeah? Okay, good. Cauchy-Schwarz. Those are the 3 sort of key theorems for this. And then there's one more thing about dot product. What's the dot product? Sorry, what's the dot product of u with itself? U dot u. Think about what would happen if you plugged it into this.
That's the norm of u.
Yep, almost. Norm of u squared, right? Because like you have a norm of u here, a norm of u here, the angle between them 0, right? So it's the norm of u times the norm of u. Norm squared. Make sense? Okay. What was the next chapter? Maybe I jumped through a few there. I can't quite remember, but let's see. So we did 3.1, 3.2, 3.3. What's 3.3? Anyone remember? I think someone said it. Orthogonality. Yep. So, what does it mean for 2 vectors to be orthogonal? Dot product is 0. Yep. U dot v equals 0. Is there anything else to it other than that? Oh, projections. Yeah. How do you calculate the projection of v onto u? Anyone remember this formula?
V dot u over the norm of u times u, I think.
I think so. I think that's right. Yeah. What does it mean if I say to normalize a vector? Say I wanted to normalize u.
It's, u divided by the norm of u.
Yep. So you're trying to make its length 1, right? When you say normalize, make the length 1. Okay. Next. Let's see. I realized I forgot to take attendance, so if somebody can remind me at like, 10:52 or something, somewhere around there, to take attendance. Okay. So, yeah, that's normalize. I think that's all of 3.3. 3.4, geometry of linear systems. Had to do with planes and, yeah.
Will we get some of these formulas on a formula sheet?
I think no. I'm under the impression no. I believe you'll have to read the announcement.
The posted formula sheet just has the dot product, vector component
Okay.
I think in the announcement, she said she's not gonna give us.
I don't think she's gonna give you much. Yeah, and I think that there might be formulas, like if there's like an important formula, she might include it like in the question,
Yeah.
but yeah, I think for the most part, she's not gonna give you much. Okay, 3.4 was planes and lines and stuff, right? If I gave you a plane, that's a plane, maybe I should make this a bit more standard, like that. That's the equation of a plane, right? It's ax plus by plus cz equals d. D is sort of like the, you know, the intercept of that. What would be the vector normal to that plane? What does that mean in the first place? Say I have like some plane. What does it mean for, like, what does the vector normal to that plane mean? Sorry?
So the line is perpendicular to the plane.
Like sticking right out of it, right? So like, if this was like our plane, right? This would be the normal vector, like sticking out, or possibly down, right? It's the same thing. So yeah, it's the thing sticking out of it. And how do I get that, the like components of that vector? Yep.
So the line's gonna have the same direction as the normal of the plane, which is gonna be A, B, and C.
Yep. So it's just ABC. Great. Awesome. Does the D matter? No, because you're just like shifting the plane, right? You're just moving the plane around. So it doesn't matter. The norm is still going to be the same, right? Cool. Okay, so if I were to ask you, does, I don't know, some vector, say it's a v1, v2, v3, if I were to say, does that lie on this plane, how would I do that? Yep.
You wanna check if it lies on the plane?
Yeah.
Do the dot product
Dot product with.
of A, B, and C.
Yep. And what should I check for?
And if you get 0, that means it's, so it's perpendicular to the normal, so it lies on the plane.
Yes. So if the vector lies on the plane, then if you do the dot product of this ABC with whatever vector you're given, then you would get, so usually we write this as like n, maybe n hat. If you do v dotted with n hat, if that gives you 0, then that means v is on the plane. Make sense? Cool. Next, cross product. How do we calculate the cross product? First off, before we even get to that, what do we need to make sure of so that we can even do the cross product? There's like a requirement for it.
Has to be in R3.
Has to be in R3, yep. So cross product, it's only defined in R3. So how do I do the cross product of U1, U2, U3 with V1, V2, V3? And I think there's a couple ways to do this. Yeah. There's a couple ways to do this, and I don't really know what they are, what the other one is. I know one of them. Anyone remember? Yep.
Write U1, U2, U3. And then right below it, write V1, V2, and V3.
Mm-hmm.
And do the same thing again right beside it.
Like here.
Yeah.
This is the way I don't know how to do it, so you'll have to walk me through it.
And then you find the determinants for U2, U3, V2, and V3.
U2, so I'm doing, sorry, this times this?
No. So can you just draw a box around U2, U3, V2, and V3?
This, yep.
And then another box around U3, U1, V3, and V1.
This,
And then U1, U2, and then V1, V2.
this.
And then you just find the determinants for all three.
Yeah, that seems right. And you subtract one of them, right?
Subtract.
I think you're subtracting one of them?
No.
No? Okay. No.
I think you just put in the determinants you found also in vector form.
Oh, yeah, that would make sense. That's actually pretty easy. I've never seen that way. Cool.
What's the way that you do it?
What's the way that I do it? I do the determinant of I, J, K, U1, U2, U3, V1, V2, V3. And that's equal to U cross V. If you do this determinant and just kind of pretend that these I's, J's, and K's are just like, I don't know, just variables. Once you get to the end, whatever's in front of I, that's your first component. Whatever's in front of J is your second component. Whatever's in front of K is your third component. That's it.
That's interesting.
It's the same thing. It's just in a different form, right? You do row, or you do cofactor expansion along this row. So you would get like I hat times the determinant of what's down there. So U2, U3, V2, V3. So it is actually the same thing as this, right?
Yeah.
And then you do minus J hat, right? Because we're now in 1, 2. So -1 to the power of 1 plus 2 is -1. So we'll subtract J hat times U1, like this thing, U1, U3, V1, V3, and then plus K hat times whatever's left in this side, U1, U2, V1, V2. And then, yeah, from there you just do the determinants and it gives you the answer.
The middle box there is flipped, so that's why there's no negative.
Yeah, that's why. That's why I thought there was gonna be a negative, but yeah, it's because it's flipped. Yeah, so whatever way you think is better, I don't know. This is just the way I was taught, so like when people start doing all the weird like, oh, draw lines and draw boxes, I'm like, okay, I don't really know how to do that. I always forget it, at least. I learn it every year, and then, yeah, then I forget. Okay. This one's kind of nice because it's just like a formula, right? You just memorize this formula and then just do it, right? You know how to do a 3x3 determinant. It's nothing new, really. Okay, 4.1. What was 4.1? Vector spaces. What are the 10 vector space axioms? Number 1. Sorry? There's 5 properties that have to do with addition and 5 properties that have to do with scalar multiplication.
First one is U and V are vectors, then there's sum has to be a vector.
Yep. What's the second one? Yep.
Plus B equals B plus U.
Yep. What's the third one? Let's do all the addition ones. Yeah.
U plus bracket B plus W equals U bracket U plus U B and then
Yep. What's number 4?
Zero vector such that U plus 0 equals 0 plus U, which is equals U.
Yep. 5?
U plus negative U equals
Yep. Now let's do the multiplication ones. Yep.
supposed to be another one where it's like, oh wait, no, that's
Oh, is it like the U in bracket times B and then B times U?
Nope, because you can't multiply vectors. KU, right? So K, if K is in R and U is in V, then KU is in V. 7?
Is there a 1 times U as well?
Yep. 1 times U equals U. 8. Missing 3. Yep, that's one of them. K times U plus V equals KU plus KV. 9? Yep.
K times bracket V times W equals U times V bracket times W.
Like this. Is that what you're saying?
No, I mean that could work too, yeah.
That is one of them.
Yeah.
Yeah, I think that's what you were trying to get at.
Yeah.
Yeah. Last one. It's another distributivity. One that everyone forgets. Yeah.
Is it k times 0 equals 0?
Nope.
Okay, plus times 0?
No. There's no. Well, that's not an axiom. Sorry.
In parentheses, k plus l times u
That's it.
is equal to ku plus lu.
Yep. That's it. Those are 10 axioms. Which two do I need to check for a subspace?
1 and 6.
1 and 6, right? Just the closures. Okay. I don't know. We did span and linear independence and basis today, so, and it is 10:52, so I'm gonna wrap up. I'm gonna do attendance, and then if you have any questions, we'll probably be done a little bit early. Once you have attendance taken, though, you can leave. I'm not gonna stop you.